Now let us design a controller for given transfer function Gp of s equal to 1 upon 3s plus 1. For that, let us design the controller. Let us assume that sampling period t equal to 1. Sampling period t equal to 1. Tau equal to 3. Tau equal to 3. For that, let us design the controller. Deadbeat controller. Deadbeat controller. The assumption made in the deadbeat controller is if the input is a step input, what is the step input in digital domain? This is the step input 0, 1, 2, 3, magnitude is 1, 4, 5. This is the step input. The response is, we are assuming that the response, this is the input y set point of z, y set point of t, y set point of k. Here y of k output is, we are assuming that if you give a step input, what we are expecting? We are also expecting a step output. But we are assuming that we are also getting the step output, but not immediately after one sampling period. After one sampling period, we are getting. This is the assumption we made in designing deadbeat controller. What is this is a step. This is a step signal in S domain. That is 1 by s. S domain, it is 1 by s. In Z domain, y set point of k equal to Z transform of 1 by s. That is equal to 1 upon 1 minus Z power minus 1. That is y set point of Z. Y set point of Z. In Z domain, 1 by 1 minus Z power minus 1. What is y of k? Y of k is, this is the response in continuous domain. That is, this is a response like this, but let us assume this way. This is the assumption. The response is like that. The response is, we are assuming that like this. In continuous domain, it is also 1 by s because it is a step signal, but a delay by one sampling period. That's why e power minus t s. If you find the y of z equal to, for 1 by s, 1 by 1 minus z power minus 1, e power minus t s, that is sample t equal to 1. One sampling period delay. That's why we have to write z power minus 1. Delay can be represented in Z domain, Z domain by Z power minus 1. One sampling period delay. Z power minus 2 means 2 sampling period delay. Like that, we can tell. So what is the difference between input and output? Input is a signal which is given at t equal to 0. Output is also a step function, but from first sampling period. The Z transform of the output is this. Input to the system is this. Here, the input to the system is 1 by 1 minus Z power minus 1. The output of the system is Z power minus 1 upon 1 minus Z power minus 1. Therefore, we can find this y of Z by y set point of Z. What is y of Z upon y set point of Z? That is equal to y of Z is Z power minus 1 upon 1 minus Z power minus 1. What is y set point of Z? 1 by 1 minus Z power minus 1. These two getting cancelled. Therefore, y of Z upon y set point of Z is Z power minus 1. You can substitute Z power minus 1 in place of this. Z power minus 1. In place of this also, you can substitute Z power minus 1. If you find this 1 by HGP of Z, you can find the digital controller. Already we assumed that GP of S is 1 upon 3s plus 1. Sampling period is 1, t equal to 1. That is tau equal to 3. For that, we have to find 1 by HGP of Z. H of S equal to what? 1 minus e power minus ts upon s. Later we'll derive this. Zero order pole derivation also we'll do later. H of s equal to, for laboratory purpose, you remember this, that's all. H of s is this. Gp of s is 1 by 3s plus 1. Therefore, HGP of s equal to HGP of s equal to 1 minus e power minus s, because t equal to 1, multiplied by 1 upon s multiplied by 3s plus 1. That is, if you take HGP of z, HGP of z equal to 1 minus z power minus 1 for this. For this, the standard formula is Z transform of 1 upon S multiplied by tau S plus 1 equal to 1 minus e power minus 1 by tau, t equal to 1. Actually, this is t by tau. Let us write like that. 1 minus e power minus t by tau, sampling period, Z power minus 1 upon 1 minus Z power minus 1 multiplied by 1 minus e power minus t by tau Z power minus 1. This is Z transform of this. Therefore, this can be substituted here. We substitute that, what you will get, 1 minus e power t equal to 1, tau equal to 3, minus 1 by 3 z power minus 1 whole divided by 1 minus z power minus 1 minus e power minus 1 by 3 z power minus 1. That is equal to 1 minus 0.716. E power minus 1 by 3 is 0.716 multiplied by z power minus 1 upon 1 minus 0.716 z power minus 1. That is equal to 0.283 z power minus 1 upon 1 minus 0.716 z power minus 1. This is HGP of z. This is equal to HGP of z also we got. Now you substitute here. Therefore, d of z equal to z power minus 1 whole divided by 1 minus z power minus 1 by HGP of z. We have to write the inverse of this. 1 minus 0.716 z power minus 1 upon 0.283 z power minus 1. So if you multiply this by z power minus 1, you will get z power minus 1 minus 0.716 z power minus 2 upon 0.283 z power minus 1 minus 0.283 z power minus 2. This is d of z. What is, if you write this in positive powers, it should be in negative powers. To realize, to understand the controller output, it should be in negative powers. So if you multiply the numerator denominator by z, what you will get is d of z equal to d of z equal to z power minus 1 minus 0.716 z power minus 2 upon 0.283 z power minus 1 minus 0.283 z power minus 2. Multiply the numerator denominator by z, you will get 1 minus 0.716 z power minus 1 upon 0.283 minus 0.283 z power minus 1. This is d of z, that is m of z upon e of z. Because why I am writing m of z by d of z is, here d of z, what is the output of d of z? Controller output, m of t in continuous domain. Here m of k. Here it is error is the input. In continuous domain, e of t. Here e of k. E of k. Here m of k. So we can write the d of z as m of z by e of z. Cross multiply, you will get, you can take this 1 by 0.283 outside and write 1 minus 0.716 z power minus 1 upon 1 minus z power minus 1. If you cross multiply, you will get m of z minus z power minus 1 m of z equal to 1 by 0.283 e of z minus 0.716 z power minus 1 e of z. If you write in time domain, that is sampled value, m of z, if you take inverse z transform, you will get m of k minus, this is also m of k, but z power minus 1 means delay by one sampling period. That's why m of k minus 1 equal to, here 1 by 0.283 e of k. If you take inverse z transform, you will get e of k minus, this is also e of k, 0.716 z power minus 1 means delay by one sampling period, that is e of k minus 1, What is the meaning of the controller? Meaning of the controller is, the controller output m of k equal to, you bring this to the right hand side, m of k minus 1 means previous controller output, previous sampling period. Suppose I am in sampling period 10 means 9th sampling time value is m of k minus 1. So m of k minus 1 plus e of k error divided by 0.283 minus 0.716 divided by 0.283 e of k minus 1. So if you know the error at the sampling instance, we can find the controller out. This is to visualize the controller out. But for simulation, you can directly enter in terms of Z domain. This is to visualize. But you can enter in directly this d of Z, you can enter in the MATLAB simulate. But this is in negative powers, it should be in positive powers. Again, multiply one more time by Z, you will get, if you are, you can multiply this by Z square, numerator and denominator, you will get d of Z equal to, multiply the numerator denominator by Z square, highest negative power. If you multiply, you will get Z minus 0.716 whole divided by 0.283 Z minus 0.283. This has to be entered there. Suppose, let us simulate all together. Before that, let us design the controller for a transfer function with delay. 1 by 3s plus 1 already we have seen. Now let us simulate for e power minus 1.125, 1.134 135, 1.135. Yes, it means what? It has the process has a dead time of 1.135 seconds. If you, for this, what is the deadbeat controller? What is the deadbeat controller? Suppose this is the process. This is the process. What is the transfer function? 1 upon 3s plus 1 e power minus 1.125 s. It means if you give input here, when you will get output after 1.12 seconds only. After 1.12 seconds only, you will get output. You will get output only after 1.125 seconds. Till then, you won't get any output. Till then, you won't get any output. So, in sampled data system, when you will get output? After, at the first sampling instant, you won't get, because sampling period is 1 second, but the process has a dead time of greater than 1 second. Greater than 1 second, that's why you won't get any output. Till then, it will be 0. This is time 1 second. This is 2 seconds. This is the time 1.125 seconds. Here, the response will be, actual response will be, first order response will be after like this, like this. This is continuous domain. This is continuous domain. After a delay of 1.125, you will get response. But in discrete domain, you will get 0 value. Here, after 2 sampling period, you will get a value. Here only you will get this value only. Therefore, the response is up to this 0. At 2, you will get a value. At 3, from this is the third sampling instant. Third sampling instant, it settled. So up to third sampling instant, this much value. This is the response. This is the response. Here, after 1 sampling period only, you will get some value. After 2 sampling period only, you are getting, because this delay is greater than 1 sampling period. So up to 2 sampling period, you won't get any output because it is sample data system. It is not continuous domain. In continuous domain, you are getting value. Before that, you are getting value. But in sample data system, you won't get, because the sampler will see only at the second sampling period only. Till then, any output comes, it won't see. Therefore, this can be approximated to 3s plus 1 e power minus 2s. Why I am approximating like that? Because we are seeing response only after 2 sampling period 1. We are not getting any output. But while finding HGP of Z, if you consider 1.125, you cannot find Z transform. Conventional Z transform you cannot find, because sampling period is 1. This is fractional value of sampling period. E power minus 1s means you will get Z power minus 1. E power minus 2 sampling period means Z power minus 2 you will get if you take Z transform. Z transform of e power minus 3s means you will get Z power minus 3. Z transform of e power minus 1.125s means you won't get what is the value? You cannot get, because it is not integral multiple of sampling period. The number delay is not integral multiple of sampling period. That's why here we are assuming that e power minus 2s. But there is another Z transform is there. That is called modified Z transform. That is called modified Z transform. In that you can get 1 by HGP of Z for 1.125. They will predict in between values in that modified Z transform. We are not going to see that modified Z transform now. We'll see that later. Now we will assume that it is e power minus 2s. By assuming that, we will find the controller. We will find the controller, e power minus 2s. Already we know that HGP of S, Z transform of HGP of S for 1 by 3s plus 1, already we know. That is 1 minus e power minus s upon s multiplied by 1 by 3s plus 1. If you find Z transform, what is that? already we got HGP of Z, already we got HGP of Z is this is 0.283 Z power minus 1 upon 1 minus 0.716 Z power minus 1. This is HGP of Z. HGP of Z without this dead time. If you consider that dead time, what you will get is Z power minus 2. That's all. Already I told you that if it is 2 sampling period, it means Z power minus 2. Therefore, what you will get is HGP of Z equal to 0.283 Z power minus 3 upon 1 minus 0.716 Z power minus 1. This is HGP of Z for a system with a dead time. HGP of Z we got. Now we have to find Y of Z. Y of Z we get only at the second sampling period only. We are getting only at a second sampling period. But we are approximating this to 2. We are approximating this to 2. That's why if you assume this is the dead time, you will get only at the third sampling period only. Only at the third sampling period. Because we assumed approximated 1.125 into 3 sampling periods. That's why you will get the value only at the third sampling period only. Because we are approximating that 1.125 into 2 sampling periods. That's why you will get a response only at the third sampling period. Therefore, what is Y of Z? Y of Z is generally you will put Z power minus 1 divided by 1 minus Z power minus 1. Minus 1 you will put here. We will get only at the third sampling period. That's why Z power minus 3, Y of Z. Therefore, Y of Z by Y of Z, what is D of Z? What is D of Z? Equal to 1 by HGP of Z multiplied by Y of Z upon Y set point of Z whole divided by 1 minus Y of Z upon Y set point of Z. Here, HGP of Z already we got. HGP of Z equal to what? HGP of Z equal to 0.283 Z power minus 3 because the system has dead time. 1 minus 0.716 Z power minus 1. HGP of Z. What is Y of Z? Y of Z equal to, that is also we will get only after 3 sampling period because we are assuming that the dead time is 2 seconds. That's why Y of Z equal to Z power minus 3 divided by 1 minus Z power minus 1. What is Y set point of Z? Y set point of Z is same 1 by 1 minus Z power minus 1. So we know all these 3 values. Now we can find D of Z. D of Z equal to, if you substitute this, you will get 1 minus 0.716 Z power minus 1 whole divided by 0.283 Z power minus 3. Z power minus 3 multiplied by Y of Z is Z power minus 3. Because Y of Z by Y set point of Z, if you divide these two, Y of Z by Y set point of Z equal to Z power minus 3. So Z power minus 3 divided by 1 minus Z power minus 3. You will get this Z power minus 3 and this getting cancelled. Therefore, D of Z equal to 1 minus 0.716 Z power minus 1 whole divided by 0.283 minus 0.283 Z power minus 3. So now we got 2 controllers, one for without dead time, another one with dead time. You can approximate the 4th order process GP of S equal to 1 by S plus 1 to the power 4 can be approximated as 1 by 3S plus 1 multiplied by e power minus 1.125S. You can approximate like that. 4th order process can be approximated like that. So this is the actual process. This is the actual process to be controlled. This is the model. This is the model. To design controller, we need the model. This model can be used to design the deadbeat controller. We design, so this can be used to control fourth order process also, because the model of the fourth order process is this. For that already we got the controller. So this can be used to control fourth order process also. Now let us see the simulation. This time. So simulation we'll see in the next class. So this is your experiment. You have to design the controller.